Hey guys, welcome back to AIT 1003. We are moving along into our next lesson. We have talked about pneumatics and hydraulics as part of our fluid power so far, and this particular lecture is going to deal specifically with hydraulics. Okay, a couple of things I want you to make sure that you're doing. I hope you're taking notes during these lectures because you're going to need them. We're going to get into some more formulas and some more concepts, and you're really going to need to take notes. So if you haven't been taking maybe quite as good notes, it probably showed up on some of your quizzes. But anyway, make sure you take those notes, understand what it is we're talking about, and if you don't, come see me, okay? Just make an appointment with me. We'll talk over the phone, or you can visit. We can visit in the lab or whatever. But these concepts, like I told you, I promised you, they were going to build and build and build, and they're still doing this. So we're going to get busy with lesson 3 here with the hydraulics. But like I said, make sure you take notes and understand what it is we're going through. Okay. All right. So first of all, we're going to talk about hydraulics specifically for this lesson. We'll get into pneumatics in the next one, but hydraulic, both fluid and air, okay, we transfer the energy of our fluid that our fluids or our air provides through the rotation of a pump or a compressor. And what we are trying to create, now this is important, what we're trying to create is flow. We also create pressure, and those two are related to each other, but our primary purpose of a pump or a compressor is we want to create that flow of either hydraulic fluid or air. And as I stated earlier, we're going to deal specifically with hydraulics, okay? Again, our primary purpose of a pump is to create flow, okay? And flow is simply the movement of our fluid through our system. It's the movement of our fluid through cylinders, actuators, conductors. That flow is moving from the pump back and recirculating into the reservoir, but that flow is what we want our pump to create, okay? And we measure that flow in GPM, or gallons per minute. That's a standard unit of measure for pumps, and so they're measured in gallons per minute. And the flow rate, not the pressure, is what determines the speed of our actuators, such as cylinders, hydraulic motors, or actuators, okay? That flow determines that speed, okay? But like I said, it's rated in GPM, or gallons per minute. I just Googled one of the fluid power sites and pulled up just this Parker pump, okay? And it's just to show you, this is a pump. It is a gear pump, and it's 5 gallons per minute, okay? So that pump is rated at 5 GPM. That's the amount it can put out when you're running at 2,000 RPM. So whatever you're hooked to, whether it's an electric motor, whether it's a tractor accessory gearbox, or whatever the case may be, this pump is going to put out 5 gallons per minute when we're running at 2,000 RPM, okay? And let's see, it is a gear pump, as I stated. It gives you a little information about it. But down here below, you probably can't read this, but I'll read it to you. It says GPM at 1,800 RPM is 4.99. That's almost 5 gallons. Well, usually a 3-phase, 4-pole induction motor, which is used heavily in industry, runs at 1,800 RPM, a little bit less actually if you count in the slip. But roughly saying this, my point is that pumps are rated in GPM, okay? And they will talk about pressure. We'll talk about pressure a little bit later, but GPM is the flow rate at which pumps are rated, okay? So flow also seeks the path of least resistance, and it also seeks to go from high pressure to low pressure. Now, I've used this image before in one of the previous lectures, but a lot of people think, and this is just to explain that, a lot of people think that when you have a straw in your cup and you're sucking water into your mouth, or whatever it is you're drinking, okay, but you're sucking it into your mouth. That's not quite true. The atmospheric pressure, we talked about this in the previous lecture, is about 14.7 pounds per square inch if you're at sea level, okay? And we'll assume we're at sea level in this example. But you got 14.7 pounds per square inch of this area in our glass pressing down on that liquid. Okay, it's not going anywhere, but it's just sitting there. What we're doing when we create it, what we're doing in our mouth is we are creating, you might consider it a vacuum, but a vacuum is a pressure lower than atmospheric. So while this is 14.7, let's just use a round number or another number. Say we're creating a pressure of 10.7. Well, our fluid is going to want to go to the highest pressure to the lowest. So what's going on is we are creating a lower pressure in our mouth than the atmosphere, and the atmosphere is actually shoving the water into our mouth. We are not sucking that water into our mouth. It is going from high pressure to low pressure, lower pressure than the atmospheric is in your mouth. And that water, the atmospheric pressure is actually shoving that water up in the straw. So I just like to use that as an example to help you kind of understand what we're talking about when we say path of least resistance and we're trying to flow from a high pressure to a low pressure, okay? But that's just a real elementary example. In a hydraulic example, in this particular system, and you should be getting pretty familiar with most of these symbols. We're going to go through some more as we go through this lecture. But we've got 3 cylinders, each one of them being fed by the same pump, okay? And they are, from what we can tell, the same size in diameter and the same size in stroke. They seem to be 3 identical cylinders. And our flow is going to come in here, and we're going to fill these chambers back behind this piston on the cap side of our cylinder. Each one of them has the same amount of volume in this area right here. So we're going to fill them, we're going to have that fluid flow, okay, into these chambers, and it's going to fill in this, it's going to fill up this chamber and this chamber and this chamber pretty much at the same time, okay? Now, when these start to fill up, the cylinder that's going to raise first is going to be the cylinder C here, because it's got a 10-pound weight as opposed to a 50 and 100 on the other 2 cylinders. So as I said earlier, it wants to go to the path of least resistance. Well, the 10-pound weight on this cylinder that it has to move is the path of least resistance, excuse me. So we are going to raise this cylinder first. Once it fills this cylinder up with fluid and strokes and reaches its maximum stroke, it cannot go any further. So it's going to build pressure, okay, and it's going to force the flow to go here. Now, our next path of least resistance is going to be 50 pounds, and it will do the same thing over here with cylinder B as it did with cylinder C. We're going to fill that chamber up. It's going to continue to flow, and as long as we're flowing, we're going to have movement there, as long as we've got the pressure to back it up, and we're going to raise that till we fully extend, and then finally, the path of least resistance is the last cylinder. It's got 100 pounds on it, and it will, provided that the pump is providing more than 100 pounds, let's say the pump puts out 500 pounds of pressure, okay, as long as we can get flow in there and create enough pressure that's greater than 100 pounds, and our pump pumping 500 naturally would be, we are going to be able to raise that, and then we will continue to raise it until all 3 of them, this one's maxed out, all 3 of them maxed out, we have no more flow, okay, we have nowhere else for the oil to flow. So we have maxed out on our flow. We're going to get to what that means to us as far as pressure in just a little bit. But my point is that we've got the flow going from our path of least resistance, or our highest pressure, to our lowest. Okay, I got a couple of different types of circuits that this hydraulics flow can go through, and they're much like electricity. They can go through a series or parallel circuits. Let's take a look at them, okay? So, new symbol for you. I'm going to point this out to you and point it here in a second with another slide, is we're going to pull the fluid into our pump, and we are going to shift our valve, and we're going to fill up 1 cylinder at a time. Once this cylinder completely fills up, okay, it's going to then fill up this chamber on this side and make cylinder number 1 stroke, okay? So these are in series, one right after the other, so one will stroke before the other does. So those cylinders are in series. Also, the components themselves are in series with one another, okay? We got our filter in series with our pump in series with our directional valve, and then of course the cylinders are in series with each other. That little symbol back there was a diamond, this one right here with a dotted line through it, okay? That diamond is a conditioning symbol, all right? By conditioning, it can mean several things. It has some type of effect on the oil, hopefully for the good too. But here's the symbol for conditioning symbol. okay, or conditioning device, excuse me. And so this next one, here we go. These are 3 different conditioning devices, okay? Now, this one is a filter with the dotted line through there. I hope you can see that okay on the screen. But it's a diamond with a dotted line, or dashed line, excuse me, but inside the diamond. That tells it's a filtration device, okay? So it's going to filter the oil or condition it by removing contaminants from the oil, okay? This one here is a conditioning device. It's a cooler, okay? It could be a radiator type cooler that conditions the oil by removing the heat from the oil, okay? Very, very, very common on those. This is a heat exchanger for systems that are in very cold environments. We route the fluid through a heat exchanger to heat the oil up, but we are conditioning it. So conditioning takes on several meanings. In our case, it could be filtering, cooling, heating. So, but all 3 of them have in common is that they're diamonds. So that is a symbol you're going to want to recognize and remember because you're likely going to see it at another time. Just give you a little heads up there. All right, and we can also have parallel circuits. All right. Now, while these components are, most of these components are in series with each other, we have a pressure relief valve that's in parallel. Also, these cylinders. We have our fluid. We shift our valve, and our fluid goes. And of course, this little dot right here means there's a connection point in our conductors. So it feeds here, and it basically tees. Some of you have worked in the lab, and you've used the T valves before, the T fittings. It tees off, and we feed both cylinders at the same time. We're feeding them both the same amount of flow. All right, so these cylinders are in parallel with each other. Okay, but getting back to flow rate, the amount of fluid that passes a certain point for every minute is how we get our GPM. Okay, so flow rate is the amount of fluid that passes a given point in 1 minute. And as I said, we express that in GPM, or gallons per minute. All right. Now, we measure our flow. Some of you might have seen these already on the trainers in the lab. Okay. We use a flow meter to measure the amount of flow. This does not measure pressure. Okay. This measures flow. And typically, these are great for troubleshooting, by the way. Okay. They give you an idea as to what your pump is doing. It gives you an idea of the flow going to our devices and things like that. So, but usually it comes into the bottom side, and this one is unidirectional because there's a scale. You might be able to see this. It goes from 5, 10, 20, 30, 40, 50 GPM. Now, on the other half is liters per minute, and we don't really use the metric too much. We're not, at least in this class, but it's a different scale. Okay, but what it is you'll see this little red line here, and there's a device in there with an orifice, and it allows fluid to push this device, this metering device, back in the back side of it up, and it raises that red line. So the more fluid that is flowing through there per minute, the more it raises the red line to give you some indication whether you're running 10, 20, 30, whatever gallons per minute, GPM, in your system. Okay. So, like I said, they are fantastic for troubleshooting because you do have pressure gauges. Flow gauges or flow meters are equally important as far as troubleshooting. Okay, and you got a couple different types of flow. All right, you got laminar flow and turbulent flow. Okay, the book covers that a little bit for you, but laminar flow is very smooth. Turbulent is just roiling inside the conductor. And whenever we have that, we have friction when we have flow. Okay. The most amount of friction is going to be, if this is our conductor, the most amount of friction is going to be on the edges, and our highest velocity of flow is going to be right there in the middle because it experiences the least amount of friction. Okay, you have bends and turns. That's why you try to keep the bends and turns in your conductors and throughout your whole system to a minimum. You don't want a bunch of 90s and a lot of sharp bends in your hoses because it creates friction. Friction is in opposition to our flow. We don't want that. Friction also causes heat, and as we've talked about in previous lectures, heat is loss, and loss is inefficiency. So we're wasting a lot of our input energy as far as our electric motor and our pump output. We're wasting a lot of that on heat. And so we don't want to do that. So we want to make it as efficient as possible. So lines that are, and conductors that are more straight, fewer bends and curves and 90s and things like that, make for a better and more efficient system, okay? But as I was saying earlier, the velocity is greatest in the center, and the resistance is greatest up against the walls, because it's like if you were walking down a corridor or a hallway and you're rubbing against the wall, that's resistance. Okay, so it's going to slow you down, so you're going to be slower than the guy walking down the middle of the hall. And it's also you rubbing up against that wall is going to, you start generating a little heat. That's due to friction, and that's wasting your effort to try to walk down the hall. So that's just a little analogy there. But that's what we're talking about as far as laminar and turbulent flow, okay? Something else that impacts the flow is clogged filters. We have some devices that you're going to work with in the lab that have orifices or very, very small passages for the oil to travel through. Undersized or improperly sized conductors, if you're using the wrong type of hose or wrong size of hose, that can really impact the amount of flow that you get, and you don't really want to create any drop in flow as a result of your conductor. So all of these things resist flow, okay? But there is a time that we want to be able to resist some of that flow. What if we want to control the flow, okay? That's what we're going to talk about next. I'm going to, like I said in passing, I'm going to keep these videos short and concise, and we're going to have multiple ones so that it's easier for you to find the information, easier for me to upload, and you know the story behind all that. So when we come back, we're going to talk about flow control. It's going to give us the opportunity to control that so that we can have some advantages in doing so. For right now, that's it. Be sure to shut this one down and start the next one, and we will see you on the next video. Thank you.